Okay? Now, what about acceleration? So here I should warn you that there's a serious discrepancy between the usual, maybe intuitive notion of acceleration, the one that you are aware of when you drive a car, and the one that we'll be using. So you might think acceleration is just the derivative of speed. You know, if my car goes 55 miles an hour on the highway, then it's going at constant speed. It's not accelerating. But let's say that I'm taking a really tight turn. Then I'm going to feel something. You know, there's some force being exerted. And in fact, there is a sideways acceleration at that point, even though the speed is not changing. So the definition we'll take of acceleration is as a vector. And the acceleration vector is just the derivative of a velocity vector. So even if the speed is constant, that means even if the length of the velocity vector stays the same, the velocity vector can still rotate. And as it rotates, that produces acceleration. Okay? And so this is the notion of acceleration that's relevant in physics. For example, when you write F equals ma, that's really what A, you know, that's the A that you have in mind here. It's a vector. Of course, if you're moving in a straight line, then the two notions are the same. I mean, acceleration is also going to be along the line and is going to have to do with the derivative of speed. But in general, that's not quite the same. So, for example, let's look at the cycloid. If we take the example of the cycloid, well, what's the derivative of 1 minus cosine t? It's sine t. And what's the derivative of sine t? Cosine t. Okay. So the acceleration vector is sine t cosine t. So in particular, let's look at what happens at time t equals 0 when the point is not moving. Well, the acceleration vector there will be 0, 1. So what that means is that if I look at my trajectory at this point, well, then the acceleration vector is pointing in that direction. It's the unit vector in the vertical direction. So my point is not moving at that particular time, but it's accelerating up. So that means actually that as it comes down, first it's slowing down, then it stops here, and then it reverses, going back up. Okay, so that's another way to understand what we were saying last time, that the trajectory at that point has a vertical tangency, because that's the direction in which the motion is going to occur just before and just after time 0. Okay, any questions about that? No. Okay, so I should insist maybe on one thing, which is that so we can differentiate vectors just component by component. Okay, and we can differentiate vector expressions according to certain rules that we'll see in a moment. One thing that we cannot do, it's not true that the length of dr dt, so which is the speed, is equal to d length r dt. Okay, this is completely false, and they're really not the same. Okay, so if you have to differentiate the length of a vector, then basically you're in trouble. If you really, really want to do it, well, the length of a vector is the square root of the sums of the squares of the components, and from that you can use formula for the derivative of the square root and the chain rule and various other things, and you can get there. But it will not be a very nice expression. There's no simple formula for this kind of thing. Fortunately, we almost never have to compute this kind of thing, because after all, it's not a very relevant quantity. What's more relevant might be this one. This is actually the speed. This one, I don't know what it means in general. Okay?